Hi, I'm Mr. True, and yes, I do have my gosh, I really care face on because possibly for you, we are going to, for the first time ever, be able to find the slope along a curved line. Now, a line or a graph that curves, you could pick any point along that curve and get a different value of slope. Here the graph is going down, here the graph is kind of flat, then it starts to kind of go up. So all along this white curved function, we have different values of slope, or the graph is going in a different direction as we let x increase from low to high values. And the purpose of math is to model the real world and predict future behaviors, or design engineering equipment like audio equipment. At any rate, many things in life do not follow a straight linear pattern. Think of how we grow. We're young, we grow very fast, and then when we get to around 18, 19 years old, we stop growing, and our height is a constant value. And then kind of starts to shrink as we get older. But that growth function is not a straight line. Or compound interest with money growing. It grows really slow, or at least it appears to be growing slowly. And then as those monetary values increase, even though we're still making the same percentage of money, same percentage of increase a year, that graph starts to slope up and have that exponential growth curve. So what calculus will do, what we're going to do is, we're going to take our old slope formula that we've been using forever, introduce this new idea of limits that we now understand, and allow calculus to tell us basically an instantaneous slope. When x equals a particular value of a, so this little dot right here, I'm going to be able to, or we're going to be able to, find the slope of that curve at that particular point. And how we do that is, well, we still have to use 2 points to find slope. So we're going to have a point defined as a value a comma f of a, basically just fancy function notation for x and y. Only, we're going to be where a is going to be the particular x value which we're going to find slope. And then there's going to be another point. But instead of just saying, well, slope is y2 minus y1 over x2 minus x1, this old slope formula is for when you have 2 fixed values, 2 fixed points along a straight line. Or here we have a green line, and it's going through this point a f of a, and this green point a, well, we're going to explain this notation in a second, but another point. This is a secant line. This line goes through my function, I guess you could argue 3 points, but I have marked off 2 points along that curve. So this green line is a secant line, and I can find the slope of that secant line using 2 fixed values of x and y. Well, okay, if I take this and I introduce function notation, I get f of x of 2 minus f of x of 1 over x of 2 minus x of 1. That's again another version of slope. I'm just introducing the function notation. But what calculus is going to allow you to do is, this slope is ever changing, so we're going to just pick 1 point to find the slope at it, or at that point. And with the idea of limits, to get the best estimate of the slope at this point, I need my other point to be flexible, to be defined by a horizontal movement of h from this point. So if I'm at A and I move to the right h units, my new x-coordinate is a plus h, and my new y-coordinate is going to be f of a plus h. Now, why do I want my second point to be defined as a horizontal distance, or described by the original fixed point, which we're going to find the slope at, and this horizontal distance? Because we're going to use the idea of limits to allow this horizontal distance to shrink, because this secant line is not a very good estimate of the slope at that point. If I could move that point a little bit closer and reduce the value of h, I have another secant line, which still we can see is going to estimate the slope a little bit high, but the yellow line would estimate the slope better than the green line. And then if I can allow that second point, because we still need 2 points to find slope, to get really close to the first point, we could have an extremely accurate estimate of the slope of this curve at that point. And indeed, with calculus, we can allow that value of h to approach 0, or allow the limit to approach 0, and basically get what we, a tangent line, a line that touches a curve at one point. You first learned about tangents when you studied circles, and actually secants as well, where you had a circle, you drew a line through it, intersected twice, it was a secant point. If that circle had a line that touched it just at one point, it was called a tangent. That's still what a tangent is, a line that touches a curve at only one point. So we want that horizontal distance from our fixed point where we want to find the slope at, and the secondary point to shrink to basically just, horizontal distance of 0.00001, approach 0. So what we're going to do is we're going to take this, we're going to have our original value of x, and we want our second point to be defined as a horizontal distance from the original one. So we're going to take out the x of 2's and replace it with, and I actually take the h's out as well, or x's, and reflect it with a. So we have, let's see, we have a point defined as a and f of a, or x and y, and the other point is going to be described from this original one with a distance of h from it. So we have, this is going to be f of a plus h over f of, a plus h, and that's equal to slope. Of course, a minus a is 0, so the denominator gets reduced to just a value of h, and now we have something that you might recognize called the difference quotient from beginning of pre-calculus. And now, if we, with now the idea, now this is all just like old school slope formula, and varying versions with different notations. If we let the limit of h approach 0, if we let the horizontal distance between these 2 points approach 0, well then we're going to get the slope of the tangent line at that point, or the slope along the curve. And we can actually find the equation of that tangent. So we're going to do 3 examples of finding slope of a curve function at a particular point, and then we'll do another video that is going to not be finding slopes at a particular point, but just give us a new equation that will allow us to find the slope along any given point. All I have to do is put in an x value, and that is called, that second video will actually be finding the derivative of the original function. And a derivative is just simply an equation that allows you to find the slope of a curved graph at any given point. All you have to do is put in the x. But we're not that far yet. So we're just going to find the slope at a particular point at which we're asked to find the slope at. Let's see what those examples look like. So here we go, first example. Now I just got done saying we were going to find the slope of a curved line at any given point. My first example is f of x is equal to 3x plus 5 at 211. We're going to find the slope of this function at this point, 211. Now you might be going, Mr. Drew, that's a straight line. I've been graphing this since Algebra 1. Well, yes. Well, I want to make sure you really see why or how or that this process actually works. This is a line. This has lines have a constant slope. We can clearly see that it's mx plus b, so this line has a slope of 3. We're going to attempt to use this difference quotient along with our idea of limit to find the slope of the tangent line at 211, and it had better come out to 3, otherwise I've made a mistake. And you're learning this process on a first question that's very, very simple, and let's make sure we actually see that 3 that we expect. Well, if we're going to try and find the slope at 211, that means that our a value is equal to 2. So, and we're also going to practice our function notation. So this says the limit, we're going to find, might need some room, let's start up here. So the slope of the tangent is the limit as h approaches 0 of f of, I don't need that, f of a plus h. This is function f. F of a plus h means I go through this function, I take out the x, I plug in a plus h. Well, a is equal to 2, so I'm going to take this function and plug in a plus, or excuse me, 2 plus h. So function f is 3 times something plus 5. I'm going to need more room for that something. This is going to be my f of a plus h minus f of a. So again, the function f is 3 times something plus 5 over h. Now what I'm doing is, especially if you're just starting in calculus or maybe you're at the very, very end of pre-calculus, students generally have trouble with function notation and messing up their signs and, I don't know, just making sure that you get it all plugged in correctly. So f, this is my function, 3 times something plus 5. Here's my function, 3 times something plus 5. In the first part of my numerator, I'm doing f of a plus h. A again is 2, so it's 2 plus h everywhere there's an x. And then for the second part, it's f of a. So I'm just plugging in 2. Okay, just make sure you watch your notation. Limit as h approaches 0 of distribute. 3 times 2 is 6. 3 times 2 is h plus 5. I'm going to do a couple of steps here because I don't have a ton of room. I want to do 3 times 2 is 6. And 6 plus 5 is 11. And then we still have that minus. So, and there might be some problems where you have to actually pay attention to that, minus sign and get it distributed through the second set of parentheses. But here we have 6 and 5 is 11. So minus 11 over h. Don't want to try and apply the limit when I get, when it becomes, or when it's going to come out to be undefined. So keep simplifying this stuff out. 6 plus 5 is 11. And 11 minus 11 is 0. So all these constants are going to cancel out. We have the limit as h approaches 0 of 3h over h. The h's cancel out, and we have the limit as h approaches 0 of a constant 3. So no matter what h is approaching, if you take the limit of a constant, the limit is that constant itself, and our answer is 3. Well, I knew that the slope of this line is 3 at every point along the function, and we've walked through what is a brand new concept, and we still got an answer of 3. Oh, well, yes, I thought I had more in the directions. So this example's done. Let's do another one. Bam! Second example. We can see this is a parabola, and we have a positive leading coefficient. So this is a parabola opening up. We're going to find the slope at 2, 3, and when we're done with this example, we're also going to take it one step further and actually find the equation of the tangent line at that point. When they give you a point to find the slope at, remember the x-coordinate is your a value. So our a is equal to 2 because we want to find the slope at 2, 3. Okay, well the slope of the tangent is equal to the limit as h approaches 0 of f of a plus h. F of. So we have parentheses, 2 times something squared minus 3 times something plus 1. That's going to be my f of a plus h minus f parentheses, okay, f of a. So 2 times something squared minus 3 times something plus 1. All of that over h. Okay. First part of the numerator, f of a plus h. A, which is 2, plus h. So 2 plus h. Everywhere there used to be a x. And the second half is f of a plus h minus f of a, which is 2. Okay, well at this point it's just a lot of arithmetic and algebra. Be very, very careful. Don't make any sign mistakes. Watch your parentheses and just take your time and watch your notation as well. Easy, 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 easy to make a mistake. Limit as h approaches 0 of 2 times 2 plus h times 2 plus h. If you properly distribute that all together, 2 plus h times 2 plus h is 4 plus 4h plus h squared. You're in calculus now, right? This is not 4 plus h squared. If you don't get this, write it twice and distribute it together. You will get that middle term. A lot of students forget that initially. Minus, I'm going to distribute this 3, so minus 6 minus 3h plus 1. Don't need that parentheses at the end. Minus, let's see, well this is all arithmetic, so again, I've got a limited amount of space here. I want to make sure I fit it in one screen. 2 squared is 2 times 2, which is 4. 4 times 2 is 8. Minus 6 plus 1. All of that over h. Now, 8 minus 6 is 2, and 2 plus 1 is 3. Okay, need to distribute this 2 through. So we have the limit as h approaches 0. Right now it would be undefined. If that h doesn't cancel out, we're going to have a problem. 8 plus 8h plus 2h squared. Well, negative 6 and 1 is 5. And 5 minus 3 is 2. Minus 3h all over h. Okay, do you see my mistake? You got to really be careful of your signs, and I'm prone to doing this as well. What do we have here? We have negative 6, now it's negative 5, and negative 5 minus 3 is not 2. I could reshoot this, but I just want you to realize how important it is to go slow and make sure that you pay attention to your work. So negative 6, negative 5 minus 3 is negative 8. Why did I pause so long and stare at it? How did I know that I was making a mistake? I know that this h is going to have to cancel out of the denominator, otherwise I can't allow h to approach 0 and become undefined. And a lot of stuff when you're doing these derivatives or these slopes at a particular point, a lot of stuff always cancels out. And this denominator generally is going to just, cancel away and allow you to plug in that value of 0. And I was seeing that my constants were not going to cancel out, so I knew that I had, done something wrong there just a second ago. So the positive 8 and negative 8 do cancel out, so we have the limit as h approaches 0 of, let's see, we have 2h squared, and 8 minus 3 is 5h over h. Now you see what's going to happen? I can take an h out of here, limit as h approaches 0 of h times 2h plus 5 over h. Those h's are going to cancel out. Now I can let h approach 0 and not have a problem with my denominator being undefined. So I'm going to go ahead and take 0, plug it in, and I get 2 times 0 plus 5 equals 5. So if we were to graph this parabola, and not that you can see what the slope is anyway on a graph, but if you were to graph this parabola at the point 2, 3, which is on that parabola, the slope of the tangent line is going to have a slope of 5. So let me just quickly, I'm not going to try and make this accurate, but there's this point at 2, 3. Here's a tangent line with a slope of 5. Let's go ahead and just find the slope, or the actual equation of that tangent line. We have the point that the line goes through, and we have the slope of that tangent line. So we have y minus the y of our coordinate, which is 3, equals m, our slope, which is 5, times x minus 2. That's y minus 3 equals 5x minus 10, add 3 to both sides, and we get y is equal to 5x minus 7. So not only have we found the slope along a curve, which is the first time we've ever done it, that's really, really cool, and we, just for kicks, found the equation of the actual tangent line. We got one more example in this video, we'll be done. Bam! Alrighty then, last example. F of x is equal to the square root of x minus 1. I want to find the slope at the point 5, 2. I can even then, therefore, find the tangent line, the tangent to this function at the point 5, 2. Don't forget, again, our a value is 5 because, well, that's the x coordinate, or x value of our coordinate. So the slope of the tangent is equal to the limit. No limit. Yes, there is. It's going to be at the limit as h approaches 0 of, f of a plus h. So, square root of something minus 1. And then something will be a plus h. Minus the square root, or minus f of a. So that's going to be something again minus 1. All over h. F of a plus h, f of a 5 plus h. And then second term in the numerator, f of a. Okie dokie. So we have the limit as h approaches 0 of, well, let's see. 5 minus 1 is 4, so the square root of 4 plus h minus 5 minus 1 is 4, and the square root of 4 is equal to 2 over h. This pattern should look really familiar because I just got done talking about when we found limits of quotients using properties. We talked about how we would fairly often in calculus, especially finding derivatives, have to rationalize the numerator to be able to find, well, in this case, the slope at the point 5, 2, or find the derivative. So, which we're not really truly finding derivatives yet, we're just finding slopes at particular points. But we have a binomial numerator, we have a radical sign, so that needs to come out because, or we need to do something with it, because if I just let h approach 0, I'm dividing by 0 and this is undefined, and I don't want to draw a graph or make a, graph this function to try and find the limit with a graph, or make a t-table to find the limit numerically. So we're going to rationalize the numerator by multiplying the numerator and denominator by the conjugate. So that basically just change the middle sign. 4 plus h plus 2, change that middle sign. 4 plus h plus 2. We're going to distribute. Being careful of our signs in our algebra. And I'm not going to distribute the denominator because I'm hoping that h cancels out. So I don't want to distribute it through and then have to factor it back out again. So we have the limit as h approaches 0 of the square root of 4 plus h times the square root of 4 plus h is 4 plus h. I'm just going to keep that in parentheses. I'm not really going to do anything. I just want to make sure I've identified or highlight that's the first term through this distribution process. Plus 2 square root of 4 plus h minus 2 square root of 4 plus h minus 4.
Attention everyone, the building will be closed at 4 o'clock. You need to exit the building by 4 o'clock today.
Wow. Okay. We had a little interruption there. So first, the expansion, right, numerator, through the distribution process is right here. Over h times the square root of 4 plus h plus 2. There we go. And now a bunch of cancellation starts happening. 2 square root of 4 plus h minus 2 square root of 4 plus h cancels out. The 4 here and the 4 at the end will also cancel out. And we're left with, well, not a whole lot. But just to, again, make sure you can follow my work here, we have the limit. We'll do one more line. As h approaches 0 of, well, h over h times the square root of 4 plus h plus 2. These h's cancel out, leaving me with just a 1 in the numerator. And, well, I can plug in 0 now and not get an answer that's undefined. So, we get 1, and we're plugging in 0 to find the limit, over, we're taking the limit of the numerator, which is a constant, and the limit of the denominator, its quotient. So plugging in 0, we have the square root of 4 plus 0 plus 2, that is 1 over square root of 4 is 2, plus 2, which is 1/4. So the slope of this function at the point 5, 2 is equal to 1/4. And if I needed to actually find the tangent line one more time, the tangent line is y minus the y of the point equals m, our slope, which is 1/4, times x minus the x of our point. Distribute that through. 1/4 x minus 5/4. Add 2 to both sides. Need a common denominator there. So we get y is equal to 1/4 x, negative 5 plus 8 is 3/4. And you just learned how to find the slope of a curved line. How freaking cool is that? Bam! Go do your homework.